So here we are with one of the, I would say, less popular, less cool metabolic pathways in central metabolism, the pentose phosphate pathway. Everyone gets all excited about glycolysis. It's the big money one. It's the cool one. But the pentose phosphate pathway, it just doesn't get the attention that glycolysis does. Nevertheless, it's very interesting. Now, the role of the pentose phosphate pathway is the first thing that we need to get squared. The role of it is to generate NADPH. Now, this is going to be used in biosynthesis of lipids later on, but it acts NADPH. We've already seen NADH. We already generated a bunch of NADH in glycolysis, but this acts as a reducing agent in a number of different anabolic or building up reactions. In addition to that, we produce ribose biphosphate. So we got two things that we're making, NADPH and ribose biphosphate. Now, ribose biphosphate is going to be the structural component of nucleotides and nucleic acids. Okay, so what this is going to do is this is a reaction that is going to occur in the cytoplasm in two different phases, an oxidative phase and a non-oxidative phase. So that's the two parts of this pathway that we're going to be focusing on. Now, this is a nice way of looking at it and super simple and saying, oh yeah, the oxidative and non-oxidative phase. Okay, great, cool. But where do I go with all of this? It seems, first and foremost, you got to start up here. But then even when you start there, you've got all these arrows, and then if you look down, this transketolase and transalbilase, another transketolase, an isomerase and an epimerase. Oh, there's just this interchanging, and where does it end? Where on earth does it end? Okay, so with that said, what I want to do is I want to highlight our two products. Our two products are NADPH, here and here, and ribose biphosphate. Now that ribose biphosphate, if you look at the arrows, it's got an equilibrium arrow. So it can still be involved in a reaction. But if you think about it as this is constant, this is a flux, this non-oxidative branch, there's constant flux of these, and many of these products can go off and do other things and be utilized in different processes. Okay, but what I want to first bring to your attention is the very first input molecules, glucose 6-phosphate, which was the same as our reaction, or our first reaction in glycolysis. If you remember glycolysis, we had hexokinase. That was our first reaction. It was not the first committed step, but it was the first step. Okay, now with this oxidative branch, one of the things that I'd like to bring to y'all's attention is that we've got 3 glucose 6-phosphate molecules. So these 3 glucose 6-phosphate molecules will all simultaneously undergo a reaction from glucose 6-phosphate, there's a typo, phosphate, glucose 6-phosphate dehydrogenase to produce 6-phosphogluconolactone, or sigma-lactone, that will be hydrolyzed with this lactonase, and then that 6-phosphogluconate will undergo another dehydrogenase reaction where we're generating NADPH. Okay, now with that said, this is happening 3 times. So we get 3 NADH here, 3 more NADPH, we get 3 more NADPH right here. So we're getting from this oxidative branch 6 NADPH. Okay, now once we have those 6 NADPH molecules that are produced, we're going to end up with this D-ribulose 5-phosphate. Now that is not our product. Instead, we're looking for D-ribose, not ribulose. And if you look at the 2 molecules, you can tell that we've got a ketone, or ketose, and an aldose. Okay, so those 2 functional groups make 2 different molecules. So ribulose 5-phosphate undergoes a pair of reactions. And keep in mind, we've got a total of 3 of these molecules that are entering. So some of it, and of course, when we're talking about this happening within a cell, it's not simply 3 molecules, instead it's a concentration of them. Some of them are going to go towards this ribulose 5-phosphate epimerase and produce D-xylulose 5-phosphate. Others are going to be isomerized to produce our D-ribose biphosphate. Okay, so when you have those two molecules, one of the things that can happen, or that does happen, is this xylulose 5-phosphate goes in two different directions, both of which utilize transketolase. One transketolase is going to take xylulose 5-phosphate and ribose 5-phosphate to make D-glyceraldehyde 3-phosphate and D-cetoheptulose 7-phosphate. So we have 5 carbons, 5 carbons. Then those two are going to be combined more or less to make 3 carbons, a 3-carbon molecule and a 7-carbon molecule. Okay. Keeping track of the numbering of the carbons is maybe one of the most important parts of understanding the pentose phosphate pathway. Okay, so we've got those two molecules that are this 3-carbon and the 7-carbon molecule, that a transaldolase will utilize those and produce D-erythrose 4-phosphate and D-fructose 6-phosphate. The resulting molecules, the D-erythrose 4-phosphate and D-xylulose 5-phosphate, can be acted upon by a transketolase to produce D-glyceraldehyde 3-phosphate and D-fructose 6-phosphate. Okay, so it's totally fair to look at this and say, but what's the point? What, like, we have these transketolases, epimerases, and transaldolases moving carbons, shuffling carbons around. What? Why? Well, for one reason, we can produce a molecule that can go on to be utilized in nucleotide synthesis. Also, our oxidative branch, the 6-NADPH, well, those guys can go on to be utilized by or utilized in other anabolic processes. The way that I've always thought about this is it's almost as if this non-oxidative branch is a good way of storing something. And it's a good way of storing, and I'm going to label this R5P. It's a good way of storing our R5P, but not as ribose 5-phosphate. So you have sequestered all of the carbons that are in our ribose 5-phosphate in so many different molecules. Simply by inputting our ribulose 5-phosphate, we're able to maintain glyceraldehyde 3-phosphate, fructose 6-phosphate, erythrose 4-phosphate, fructose 6-phosphate, glyceraldehyde 3-phosphate, cetoheptulose 7-phosphate, and xylulose 5-phosphate. Not to say the only one that's utilized, but that ribose 5-phosphate, as you deplete the available amounts of ribose 5-phosphate, well, are you really running into a problem? You're not. Why? Because you have this, and I'm going to erase some of this stuff so I can make it a little bit more clear. When you deplete the cell of your ribose 5-phosphate, all that you have to do is replenish it by using some of the available glyceraldehyde 3-phosphate and cetoheptulose 7-phosphate to basically put that supply back to where it needs to be. Those carbons are there, they're just arranged in different ways. It's almost like you have these, I don't know, I can't think of a good analogy. I was going to go with a cooking analogy or something, but you have all of these different ingredients that are just the thing that you want, but rearranged. So you have that resource, you have that D-ribose 5-phosphate, even when you don't have it. So even if the ribose 5-phosphate supply has been completely depleted, well, don't worry, because you have all of these other carbons, or all of these other molecules, which have the necessary carbons so that you can replenish that store. So that's an essential molecule that you can always kind of go back to. In addition to that, you can utilize D-glucose 6-phosphate, a product of hexokinase, and generate tons of NADPH from that. All right, well, that's what I wanted to say about the pentose phosphate pathway. I do not expect that you have the pentose phosphate pathway memorized in terms of the interchange of the molecules, but I want you to understand the purpose of it and kind of a, like, what value does it bring? And when, I want you to understand that when one molecule has been completely depleted, well, what can you do? You have these transketalases and transallylases that do all the work to basically put it back together. All right, well, I hope this is helpful, and I'll see you in the next chapter.